All right, refraction is the bending of light caused by the change in speed. When light goes from one medium to another, say from air to water, if it comes in at an angle, what happens is that it's traveling at a different speed as it moves through the substance. So it bends. We always measure angles with respect to a normal line. A normal line is drawn perpendicular to the surface at the point of contact. The angle that it comes in at, and the angle that it goes out at. Theta I in this case is known as the angle of incidence. It's the angle that the light comes into the substance. Theta R in this case is the angle of refraction. The light travels, that's the new angle at which it travels through the new substance. Now it could travel in the opposite direction. It could come from water to air. In that case, the angle of refraction here would actually be increased. Now, how much it bends depends on what the speed change is. The speed in any substance is defined by the index of refraction of that substance. The index of refraction, we're going to use the symbol n for that, so lowercase n. And every substance has its own unique index. Air's index is 1.001 or something like that. Basically, you can assume that air is like a vacuum, 3 times 10 to the 8th meters per second. But when light travels through a substance like water, which has an index of refraction of 1.33, then the light slows down. How much does it slow down? According to the ratio C over V. So light traveling in water, 1.33 equals speed of light, 3 times 10 to the 8th meters per second, over the velocity in the substance. And so that velocity is whatever 3 divided by 1.33 is. 2.6 times 10 to the 8th meters per second. So it's still really, really, really fast. But it has slowed down enough to bend it. Now we went through a couple different indexes of refraction. Don't forget 1.33 is water, basically acceptable value. Glass, it's roughly 1.5. We'll confirm that in the lab tomorrow. Or hopefully you will confirm that in the lab tomorrow, if you do the lab right. Actually, our glass tomorrow, I've found over the course of 7 years, is 1.55 on average data. So that's what we're going to shoot for. That's what you will shoot for. Now, a couple rules that you have to remember. When you move from a low index to a higher index, light, a wave rather, or the ray, the light itself will bend towards the normal line. So when the light ray comes in here, say we're going from air, which has an index of 1.0, basically, to water, which has an index of 1.33. You're going from a low index to a higher index, so it's going to bend towards the normal line. That means, in this case, theta I is going to be greater than theta R. That is always the case when you go into a higher index. You always bend towards the normal line. When you move to a lower index, the reverse is true. Move to a lower index, bend away from normal line. So say we go from glass into air. Comes in, bends out. So in this case, theta I is going to be less than theta R. As you move from a low index to a higher index, you bend away from the normal line. Now, suppose that you're going from water into air, or glass into air. Water doesn't make any difference how we do this, but there's your normal line. And you come in at, say, some theta angle that way. Now we go from a high index to a low index. What happens to our ray? It bends away from it. What if we increase that angle a little bit? Now, what do? Bend even more away. Well, we're getting closer and closer and closer to that flat line. So eventually, we will have an angle that we come in at which refracts at an angle of 90 degrees. So when the angle of refraction here equals 90, that is a special angle to us. That is called theta C, or the critical angle. When you reach the critical angle, the light no longer leaves the substance. So a light ray that's shown on the border between water and air will be reflected along the border. So if you were looking at it from the outside, if you're looking at it from up here, or trying to look at it from up here, you would not be able to see the object at a certain angle because the light reflected from it or coming off from it would not exit the water. If you've ever been into the bottom of a pool and you looked up at the top of the pool, you've probably noticed that you could see the sky, but then there's a point where it looks like a reflective surface. When you go above the critical angle, say you've shown a light or a laser beam that's higher than the critical angle, some angle greater than C, what happens is that the light isn't reflected at 90 degrees, but in fact, it's reflected back into the substance. So above the critical angle, the surface between the two mediums acts as a mirror. So at this angle of incidence greater than theta C, the angle of incidence is equal to the angle of reflection. It no longer refracts. It doesn't go into the new medium and bend, but it reflects off the surface as if it were a mirror. Anywhere below the critical angle, you have normal refraction. Snell's law. When you go above the critical angle, then you have reflection. Law of reflection. Theta I equals theta R. So how do you calculate what a critical angle is? Well, if you remember what Snell's law, it's called Snell's law. It relates the index of refraction to the angle of incidence and angle of reflection. Well, at the critical angle, your first angle, what's the refraction angle? 90 degrees. So at the critical angle, it becomes sine of 90. Sine of 90 is just 1. So the result is n1 sine of the critical angle equals n2. Critical angle equals n2 over n1. So you can calculate the critical angle just knowing what the two indexes of refraction are. So it differs from where you're going to where you're going into. So there's a different critical angle from water to air than there is from glass to air, or glass to water, or diamond to water, or any two substances. So there's a sample calculation. What's the unit theta C between air theta c, or sine theta c, is n2 over n1. If you're going from air to glass, air is where you start, and glass is where you're going to. So glass is 1.5, air is 1.0. What is theta c in this case? Inverse sine of 1.5 over 1.0, which is inverse sine of 1.5. Anybody know inverse sine of 1.5? It does not exist. Very good, geometry people. It does not exist. Sine is restricted between -1 and 1. So there's no such a thing between air and glass of critical angle. That's because we started in air and we went into glass. When we start in air and go into glass, what happens to the angle of refraction? It gets closer. So it doesn't matter how steep I make this, it's always going to bend towards the normal line. Light will always travel from air to glass. It's when we do the reverse that's the problem. When we move from glass into air, we're going to start glass into air, we're going to start bending towards the normal line, and eventually there will be a point where we refract along the surface. So going from a low medium to a high medium, there's no critical angle. It's only when you go from high mediums to low mediums, or indexes rather, that you have a critical angle. So what is theta c between glass and air? Start from glass, and you go into air. Sine theta c is n2 over n1. In this case, we're going to start from glass and go into air. So theta c is inverse sine of 1 over 1.5. 41.8 degrees. So if you get to an angle of 41.8 degrees, that light will reflect along the surface. What happens if you come in at an angle of, say, 50 degrees? It will bounce off at what angle? At 50 degrees, it will bounce back into the glass. You always have to be wary of the angles when you do these problems. If you end up with a does not exist on your calculator, you're probably doing the problem right, but you've just gone past the critical angle. Just be careful about that as you go through.